Okay, so hello everyone. It's a pleasure to be here and present some of my work and also discuss in my case, how do we get from equation to the code. And I'm computational chemist. I will be talking about the computational chemistry case, but I hope some of the information that you will hear will be also helpful for you, even if it's not a computational chemistry or some other domain. Anyway, typically the problem size that you will be working on, the equation might be different or maybe similar, and then the way how you're going to approach the problem, how you're going to solve it, will really depend on the various factors, such as, for example, same size and what's the nature of the problem. So you really need to ask some questions about what the nature of the problem and what's the best way to approach it. So in general, I try to some typical questions that can be asked in general for any type of problems that you are going to work on implementation or coding or porting or optimization. What is the scope? That's the main question. What's the right computational model for my science problems? Or maybe it's the grid-based approach, maybe it's some basis set in computational chemistry, or maybe it's plane wave, or maybe something else. Maybe it's what type of theory I really need to do that, and what's the nature and then the scales of the problem. So what's the size of the problem? How big is the problem? Do I need a laptop, or do I need to do this on a cluster, or perhaps on some petascale sorting? So of course, the related problem is what's the scaling, right? So if you increase the system size, how much the computational cost of your problem? For example, if you increase physical computational chemistry and electronic structure calculation, typical scaling would be like a cubic scaling. It would mean that if the system size from, let's say, 100 from the matrices which are 100 size, and let's say it takes 1 second, and if you increase it to 200 by 200, then our computational cost is cubically, then it would the cost increase from 1 second to 8 seconds. And if we increase even twice bigger, twice larger, from 200 to 400, then it would be not 2 seconds, but 18 seconds. And so quickly, the problem size can quickly be larger than we can do. And those are the cubic scaling in electronic structure. Those are rather low costs, and then you can run into higher scaling costs at 7th order, that cluster theory. So we always want to know what's the scaling of the method, to know to know how large will be the problem that we can really think of. So if we know that this information, then we can ask what's the data structure when we are implementing our code. Can we come up with some tricky way to partition the data, maybe to partition across different computing nodes, or maybe do something that will be useful for the computational cost? What's the data structure, right? What's the cost? So which part of the cost is the most expensive? We don't want to spend the time and effort on something that is really cheap, even if it doesn't cost. It takes only 5% of our time. We want to rather identify the most expensive part in the code, and then sits with optimization those parts. So in general, what we find out, the related question was about what are the building blocks. Can we rearrange somehow the algorithm, the method, or maybe come up with a different alternative approach in which we faster? And then, of course, when we know information, we can then try to play with compiler flags and change libraries, and then if we have some efficient libraries, we can replace our handwritten code with some efficient libraries, or maybe find some optimization. But those are like towards the end of the Sometimes when you're working on your problem, you can enter into the problem on different in different stages, in different phases. So maybe you don't need to worry about the scope, because the scope already defined by your PhD advisor, or maybe you just got the code, hand out the code, and you just need to compile it and then run it. So So in the case, then you just start from compiler flags and efficient library building blocks, right? So if you're in the situation when you have to modify the code and just modify the code, and you just parallelization or optimization, then perhaps you just start from the question number 43, right? And then if you have to start with working with the question, then you really want to start from question 1: what's the scope, what's the size, scaling, and then what's the right computational model. Okay, so let's go to the next slide. I'm going to discuss the molecular dynamics approach, and here is just a brief overview. So my approach of nuclei and electrons, right? So those are molecular dynamics. Various approach for molecular dynamics are quite popular on XSEDE approaches, on XSEDE resources, especially here we can see the methods that work on the classical molecular dynamics. This will be the first column here, parameterized some Born-Oppenheimer dynamics, in which we also electrons and nuclei at the same time, and we're interested in some related properties. Or we can also talk about time-dependent quantum mechanical approaches for electronic structure, right? So the cost, in general, the cost and the problem and the tractable problems are really dependent on the type of the approaches, right? So, for example, parameterized force field, we don't have actual electrons in there, so that we can use relatively. So we don't use if we don't have electronic structure, then we don't need to spend on that, and we can really run very large simulations on over a very large system. So a very long simulation of a very large system. If we need to treat electronic structure, like in Born-Oppenheimer case, on dependent quantum mechanical treatment for electrons, then we really need to calculation. Our computational costs are really depending on the computational cost of these electrons. How do we treat electrons? So to give you some example, you can, in some case, we are interested in studying maybe molecular system of 100 to 1,000 atoms, and then the computation, as I mentioned previously, cost, the scaling is determined by the cost of electronic structure. And the reason for this method is because we want to have to model problems such as electron transfer, and this is on the time scale, structural changes on picosecond time. So we really want to have both. But the main challenges is because the system, those problems are relatively large for the dynamics and then quantum mechanical approaches, and we want to have electron coupling. And to give you an example, if we would, how expensive can that be? How challenging this can be for simulations? If we want to if we can afford 4 minutes per one MD step, per one molecular dynamic step. One molecular dynamic step would be approximately calculating the minimization of electronic structure. So 4 minutes times 10,000 time steps gives you one more, approximately 1 month. So we are, and it is not really very much for electronic structure methods, right? So we need to be careful about how we are doing and what we are doing. Okay, so next slide, equation of motion. So those are our basic equation of motion. What we want to start with X here would correspond to the position of nuclei. So we want to find the changes in the dynamics of nuclei, and the related there is a velocity for of the nuclei v. We want to integrate that, and then of course in order to move the nuclei, we need to find the forces, and then so we can propagate along this according to classical equation of motion, right? And then the forces depend on the v, where v really depends on the electronic structure, right? V, which is a gradient of the electronics of the potential energy. So in order to be able to move our nuclei forward in time, we need to find first the electronic structure. So here we want to, there are two, as I mentioned at the beginning, in talking about the different dynamics approaches. So we can either, in a Bonheimer, we can either proceed with Bonheimer approach, in which we minimize the electronic structure, or we can integrate it with time. And here we are more interested in integrating with time. So therefore, we need to solve time-dependent Schiller equation. So we fall into category of quantum dynamics, right? So again, in this time-dependent quantum mechanical time-dependent Schiller equation, we can represent the electrons can be treated in various ways. Can be treated maybe in two plane waves, or maybe on the grid, on some mesh, or through the basis set. So the most popular approach in chemistry is typically a set, and integrate this time-dependent Schiller equation along the Newton equation for nuclei with time, starting subject to initial conditions, that is position of nuclei, velocity at time zero, and initial electronic structure. Here we use a density matrix, in which density matrix to represent electronic structure. So this is basically electronic density matrix. So to summarize what we need to do, the skills that we need to know is how to calculate the potential energy. That's the first most important part. How to calculate the potential energy of nuclei from the electrons. So we need to be able to find the time dependence of density matrix, and then from that we need to calculate the forces. And for all these calculations, we need to know how to propagate density matrix. So I will just focus today. I will just focus on the calculation of the density propagation of density. So next step. So those are our basic equations. Those are our basic equations: time-dependent equation for electrons, quantum dynamics of density matrix for electrons, and Newton equation of model for nuclei. So to give an idea about the system size and the problem size, we want to deal here. To use some approximate. Always, whenever you are whenever we are solving some problems, there are always associated some estimation and simplification. So we use some simplified methods. I will talk about this for electronic structure, and then in order to give you the idea about the problem size, so we want to use maybe from 100 to 1,000 atoms, and then the T corresponds to density matrix, F corresponds to electronic Hamiltonian matrix, and this is we use the atomic orbital basis set, as you can see here on the right bottom side. We use this, so the Hamiltonian matrix F and N would be given as integral over the space of the basis function, right? So in case we don't need to worry about this. Let's assume this is given by some library, so we have some black box type machine, and this is not expensive, but still the most expensive part is propagation of density matrix. So there is a way that we can come up with some magic we just call it, and then it gives us the elements of the matrix F, and this matrix is the size of approximately few thousand, let's say 3,000 by 3,000, and same size is for the matrix P, also 3,000, 3,000, let's say approximately 3,000 to 3,000. So that's what you can expect. And the vector of position is for one atom that will be about 300 coordinates. So we have 300 because each atom has 3 coordinates, so 300 size of the vector. So here is the approximate approach for all the structure. So some method in which we don't need to worry about the core electrons. We use we have only valence electrons. I just show you slides so we know we know what is the approach to be used, and then the basic expression for energy is this first 3 equations, depending on the level of approximation, and then those equations can be converted into matrix form. So this is basically matrix form. PR corresponds to trace, right? So the sum of the diagonal elements of the matrix. So H is the Hamiltonian, single electron Hamiltonian, and G would corresponds to electron-electron interaction. Okay. So computational cost, and when I did the profiling, so for our problem size, the computational cost is is basically spend 80% on the evaluation on electronic structure, right? So the single most expensive part. Then on the propagation of density and evaluation of the forces approximately 15%, and out of this there's also significant cost related to use the electronic structure. And the remaining part is just a few percent. So handling formation of matrix. So how much it costs. And we handle matrices, and then linear algebra matrix operation are the most expensive. So we see that the cost for a single step is about 300 atoms, would give you 28 seconds, 600 atoms, 230. And you can see about almost 10 times, less than 10 times, it's actually cubic scaling. So increasing to 960 atoms, we get 1 second on multi-core. And I think it was Xeon 8 cores, on Xeon 8 cores. Overall, this is over 10 minutes, right? So we cannot really run anything that would take 10 minutes. You must remember 4 minutes times 10,000 steps. So we cannot really use that. That's really expensive. What can we do about that? So let's first talk about the equations. How do we solve the equations for this time-dependent Schrödinger equation, right? So we start from this matrix equation. So P is a matrix, say 3000 by 3000. Then F, so we have depends on time. This CH is a complex equation. So we have imaginary times, Planck constant, and then time depends on T. And then F, which will be this Hamiltonian matrix, right? The Fock matrix. So it's also the same size as the matrix. And F is the square bracket corresponds to commutator, so it basically means F minus F times T. So the first solution is given through this time evolution operator. So U of T, and then to find it, we need to find integral over time of Hamiltonian matrix, and then get the exponent of that matrix. It basically can be done through diagonalization, but I will try to show you, explain you how we can do this without diagonalization, but how to just convert this equation into matrix multiplication algorithm. All right, so we start the overall. So the solution to this density matrix evolution equation is given by this equation, right? So we can do that iteratively. So how we can do that? Right? Let's say we navigate from time 0 to time, I put here time t, but let's say it would be time delta t. Right? So if I know how to propagate from time 0 to just small tiny time step, then I can continue iteratively. Then use the propagated time to put back here into this equation, and then get back to the next to proceed to the next time. All right. So let's assume I have a initial density matrix at time t, at time 0, initial density matrix given to us, and then we can somehow find this omega operator, and an exponent of this omega operator is given by the corresponds to this time evolution operator. Right? So the is minus IH over the integral. So how we can do that? So in principle, this is the solution, right? So we can calculate so basically you can see this as 3 matrix multiplications. However, this is not that trivial, right? Because we have exponent, right? We have exponent of some omega matrix, and omega is not just a matrix, it's just all of the matrix, right? I need to find the exponent of that, right? So there are 3 ways. In principle, there are 2 ways of doing that, right? So we can find we could diagonalize omega, get the eigenvalues, the form, then based on the eigenvalues and on the eigenstrings, inform the exponential operator, and then the point the Hermitian conjugation of the same operator. So this matrix is Hermitian conjugation. And then once we know this omega, this exponent of omega, which is a unitary matrix, we can then multiply do 2 matrix approach, and then omega, here is the expression for omega in the first term of the Magnus expansion, right? So the integral, so we can matrix 3000 by 3000, so we can basically integrate each we would need to multiply, integrate each matrix element separate, right? So once we know how to integrate each element separate, then we know this omega factor, then we can plug in into we can diagonalize and plug in for exponential operator. So, but we can do the difference. We can look at this problem, and then we can insert, if we insert in this first equation, if we insert lambda, let's just fictitious parameter. Let's say we know matrix, we know our density matrix at P0 is given to us. Then we say, what if we put the exponent some parameter lambda, right? Let's say it's parameter lambda. I can insert it here. I'm free, right? And I know that I'm free to do it. And I know if this lambda is equal to 0, the exponent of 0 is equal to 1. So I should get back my P0, right? So I should get back my density matrix of time equals 0. So nothing really happens, right? So I insert here and I insert here. For lambda equal, I should get the same density. But if I include lambda equal 1, then parameter, then for lambda equal 1, I will give exactly exponent of omega times P times exponent of omega conjugation, right? So that would give me P at time T, right? So how do we do that, right? So let's say we insert our fictitious auxiliary parameter in our equation, then we can try to find the solution for P lambda. So what we want to do, we want to find the solution for P lambda equal to 1, knowing with the value of P for equal 0, right? So that's a typical problem for the Taylor expansion, right? So the Taylor expansion is given like here, so we get infinite terms, and then our lambda parameter here, and we want to find the derivative of P as a function, in this expression as a function of lambda, but we want to use it derivative for at value equals 0, right? But how do we do that, right? Then we have also our lambda k exponent and then factorial of P, right? And then we sum the terms should supposedly vanishing with the time, with the increasing number of K, right? Okay. So again, so we do derivative, and then how do we the derivative of this? Right? So this is just a reminder. So, if we have derivative of a function that is a product of different function, I wrote it in such a way that it's very similar to our P of lambda, right? So this is our P of lambda. I use x here. Our x is lambda. So we want to have three terms. This fx, which corresponds to this part exponent of lambda omega, gx, which corresponds to the third term, and then a doesn't depend on x. It doesn't depend on x, and we can just P0, right? Take derivative of this, then we want to take the mathematics smart tell us that we have to do since we have only two terms, since we have a product of two terms that depends on x, we would have sum of the two products, right? We have a derivative of the first term that depends on x times the other products, times the other elements, components, the other terms, plus our first function fx unchanged times the derivative of the of a and times the derivative of the last function, right? So when you get to our density matrix, when you apply this to our approach, and here is also we can look what happens when we get derivative of this exponential matrix. We still don't know. We still haven't done anything with it, right? We're just on the paper pencil, right? So the derivative of alpha omega, we know this is the same function times since it only depends on alpha, and alpha is scalar. So we can we know that this would be exponent of alpha omega times omega, right? Because omega itself doesn't depend on alpha, right? Oh, sorry, on lambda. So we can either then one more important observation is we can put omega here either on left side or on the right side. In general, for the matrices it's not the case, but since our omega, our exponent of matrix depends purely on omega and doesn't depend on any other matrices, then we know we can do that because those two matrices we know that they are so-called commute. So those two matrices commute, so we can do that in this particular case. Okay, so when we do that, when we apply this our expression for the first term, what we are going to get is so we apply to this term, and then what we get. So now we are going to have two terms, right? So the first term there will be derivative. So we're going to have exponent alpha, and then we are going to still have the two exponents. We're going to still have two exponents, and there will be some sum of the parameters. We can conveniently write this expression as exponent alpha lambda omega times something in this parenthesis and time expanded. But we remember that we wanted to find our solution is for the equal to 1. So now replace this and go back to our equal to 1. So when we do that for lambda equal to 0, because we need to find derivative at lambda equal to 0, right? So when we put here 0, we just end up these two terms here disappear, and from Taylor expansion we are going to get only this study. So so now you can do that for with any other terms. You can apply this recursively. So that would mean we apply the derivation to the second in the second term. Find the second term as a derivative of the first term, right? So that was the first term as a function of lambda. So this is our full function of lambda. So we take a derivative. So we do this again. Now we treat a as this whole thing in parentheses. We can treat it as a, right? So again, we derivative of this times everything else plus this part times derivative of this, right? So again, we are going to get a two terms, but our so if we get we end up with similar expression. However, this p1, our p is slightly different because it was the function from the p1. So in principle, we can do that recursively with as many terms as we want, and we end up with so-called but we always need to remember that at the end we want to put lambda equal to 0. So we do that, we end up with so-called Baker-Campbell expansion. We can so when you make all these terms P1, P2, P3, we need to end up with this type of expression, right? So this is our first commutator term, this is our second term, etc., right? So those terms will be probably going to vanishing, and then we can stop after we check that was the value of the main at the end. Okay, so let's do the next slide, and then on the next slide. So how our algorithm may look like, right? So let's say we want to propagate. We know we have the initial position of our nuclei. We have initial velocities for our nuclei, and we have a initial density matrix, and we somehow need to propagate the density matrix to the next time step, right? So we know we form this omega-1 from the as integral. You can see this is A0 initial, H0, so it's average Hamiltonian, H0 at time H0 and time at time H1, and then we multiply by time step, and then we divide by H, right? So this is basically this integral from the beginning. So this integral over the matrix, right? So this is a matrix, right? Next step, to propagate density matrix from P0 to Pp, we first, in the first step of our Taylor expansion, we just copy this one, this P0 to Pp. Then we have to somehow correct it, right? So we apply our Taylor expansion. So we use our C1. We find what is the first term commutator. Then we have to scale it. I think yes, we scale. In our case, k is equal 1, so we just scale it by 1. Right? So we have to scale it, and then we add it, right? So we replace our corrected our density matrix. Those subscript correspond to iteration in the solver, right? So we improve it by adding some correction term C1, which corresponds to this commutator, right? But we keep the C1. Instead, we calculate the next correction of the C1, and again on the similar commutator, right? So we can do, but now we have to scale it to the second term in the Taylor expansion. So we need to divide this by 2, right? So the previous term C1, we need to divide it by 2. So when we're done with C2, when we found the commutator, we add this to our density matrix 1. This commutator, we add this to our density matrix 1, and we update our propagated density matrix. We're still talking about the same time step, but we're just improving our accuracy of our electronic structure of our density matrix. So when we can with the second step, we can continue that. We can find we can use that C2, the matrix C2, to calculate, and we have our omega matrix form, so we can calculate this matrix times product, and we can calculate our correction C3, scale some factor that is from the Taylor expansion, and then we can update. We think this until we find that the matrix elements are very small with some initial threshold. Some initial threshold. So okay, so this is just the basic summary of the theory, right? So we use the Magnus expansion, and basically the theory tells us that we want to use something like this type of integral of the Hamiltonian, but in our case we are using only the first term, that is this one. When we do that, we have just the simple expression for the delta t times h0 plus h1 divided by IH, right? So this is our omega, this is our approximate omega, and we can plug it in back into our commutator expansion. So that's the final expression that we want to implement, right? Then again, this square bracket is a commutator. It's a commutator, and we calculate as AB times minus BA, right? So the commutator between matrices. Right, so it's always helpful to analyze before we start implementing. It's always helpful to analyze the structure of our data. Is there something that we can really make our calculation can benefit? Is there something? Are there any tricky or traps that we can fall into, right? Or what can we get? So it's always good to analyze on the structure of the data or the matrices, or to know what is the best, to find the best libraries and what's the best subroutines we can use, right? It turns out that in that case we deal with density matrix and with Fock matrix. And those matrices are complex. The matrix is always complex, and it's this like form, right? So it's a Greek and it's Hermitian, right? So basically the part is symmetric, and then imaginary part is anti-symmetric, right? I is imaginary part. You can see the part is 0, and then lower triangular part are the opposite sign of the upper triangular part, right? So in propagation, then the matrix U is supposed to be unitary. So there are, if we know of our problem, we can always come up with the experience that we can always come up with some and we can test if our approach is correct, or if we are not getting some problems. It's always helpful with that. So for example, we know that the square of the matrix at any given time, if the matrix is at time equals 0, so-called idempotent, that is the square of the same matrix is equal to the same, if the square of the density matrix is equal to the same matrix, then the density matrix should stay idempotent for at any given time. So those are like the situations, the ways to test the validity of our approach and see if we are getting any problem. So what's the scaling of our method, right? So we know that the density matrix E, and then since this commutator is basically matrix multiplication for the dense matrices case, then what we can expect, the dense matrix scaling is typically at third order, so we can expect that there is a typically third order. Then if we do a little more work and we can analyze what the can we benefit by using some sparse methods, or can we see what the structure of the data inside, then we probably can come up with some even lower scaling, with some lower scaling methods. Because the S matrix, this Hamiltonian matrix, is typically sparse. If our problem is very large, then we could have a sparse matrix, and this would mean, since we still want to have probably a full density matrix P, then we can expect that we could come up with some quadratic scaling algorithm, or even linear scaling if our density matrix would be also sparse. But those so this type of checks and tests always helpful and can always give good insight into future work and where should we invest our time. Okay, so let's just go back to our questions. Right? So do we need to range algorithm? How do we are now? We are done with the equation part. Now we want to talk about some implementation a little bit, right? So how to amend this in our field, right? So because again, so what is the problem size that we want to attack? So the problem size is probably 2,000. The matrices are about 3,000. let's say approximately 3,000, right? So what's the data structure? Is there any special structure or patterns to our data, right? So we know a bit about this, right? We already know a little bit. We know that the density matrix is Hermitian, and we know that the real part is symmetric, and then imaginary part is skew symmetric, and then the cost, and then we also know that perhaps F can be the functional matrix can be represented in a sparse representation if we have large enough system. Okay. So what is the expensive operation? So we did that test. We tested it. We know that the linear algebra related to propagation to electronic structure calculation. So we are also interested in compiler facts and long-term outlook. What is the outlook for the improvements and the hardware changes? We don't want to spend too much time that if we know that the code perhaps will not be valid in a year because there will be some dramatic changes in the code. So we want to spend our time wisely and then try to make the code to be weak and ready to be used in more than once and probably in a as long time scale as possible. General overview of the algorithm. So I'm here the most expensive part on the blue. So we start from initial position. The left part corresponds to the classical part of dynamics. So classical nuclei. So we start from position of nuclei and the velocities. So we need to provide the initial electronic structure. With the electrons, we need to find. We want to move. Sorry, not electrons, nuclei. We want to move our nuclei. For that, we need to find our forces. And we use this time-dependent Schwinger equation to find the forces. This is based on electronic structure and time-dependent Schwinger equation. When we don't know the forces, we can move the nuclei. We move the nuclei, we go back. For position of nuclei, we can propagate we can find the new electronic structure, etc. Right? So this part is the most expensive. So perhaps it would be beneficial to put it on GPU, or how do we make the most benefits of our how do we can get it in a smart way? Perhaps we can come with some hybrid CPU GPU implementation, so we can our calculation faster. Maybe we can connect some of our maybe Fortran code with some new with some excellent libraries, and then port patch after we identify what are the most expensive parts. Right. So so this is our approach. Right. So in principle, what we want to do, we want to offload the most expensive part to GPU while keeping some cheap part on CPU. And in our case, since we are using this time binding approach, our CPU cost is really small compared to the matrix operation. We know that the matrix operations can be really done in parallel, and particularly for this problem size, 2,000, 3,000 times 3,000, we can really benefit from GPU, right? So perhaps we can do this expensive propagation of electronic structure on GPU while keep the cheap part on CPU, which are better for CPU than for GPU. Okay, so here is just the overview. Okay, let's do a rethink of the algorithm. This is our general algorithm. This is the equation we want to solve. This is our solution. And we have to find the commutators F times P minus P times F, right? So this is what we want to find, and then but you can see here that we have two matrix multipliers, right? So that will be F times P and minus times F. So the first question is we can implement it using two matrix multiplication, F times P, and then followed by this P times F and subtraction, right? So perhaps we can do this way of doing this. Another way, if we look into the structure of the data, then we can realize that since P is really Hermitian contains two parts. One is the real part is symmetric, and the imaginary part is anti-symmetric. So perhaps we can come up with a replacement in which instead of doing the two complex matrix multipliers, perhaps we can use that formation and we come up with the smarter algorithm. It turns out, after analyzing the different cases, we analyze different cases. It turns out that the best approach would be to split our complex matrix into two blocks, one real blocks and real blocks separately and imaginary blocks separate, right? And then we test here just the approximate cost. And instead of doing two matrix multiplies, we can come algorithm in which we have single multiply and followed by transpose and subtraction of the matrix multiply, right? So this is the general cost. Turns out that the multiply is significantly secure order. It's much more expensive than corresponding transpose. So yes, matrix multiply is much more expensive than the transpose. So it's much more it's better for us to use here in our code to use this single matrix multiply version. Compare there are also other, we can repeat that when we move our density propagation to GPU, from CPU to Fermi, and then here, then we come up, we are getting about like 10 times speed. That's just this equation. We can also send some other components. That was the first step. So we can so our initial time step for if everything be done on CPU, we get about 140 seconds for I think it was for 2,200 for about 300 or 400 atoms. So for that certain size, we come up from overall we can reduce our time from 242 seconds on multi-core CPU to 24 seconds on Fermi GPU, right? So it includes not only this propagation of electronic structure, but also some other operations. So this propagation was done with we used Douglas library for matrix multiply combined with some matrix transpose on using small CUDA code. Together combine this with Fortran code. Right. Overall, here is some comparison on what happens for the most expensive part if we would like to use Kepler, right? So if you would like to use Kepler, then again this is just general comparison. So for CPU part on using 8 cores, we reduce for different system sizes. And this is the number of gigaflops. And then if we use as a base, since we don't, if we use as a base MK version, which scales very well here in our case, then we can see for this we can obtain approximately the number of gigaflops. It's about right. This is the number of gigaflops from 76 to almost 10 times if we move to Fermi, and about 30 times if we move to Kepler, right? So this factor is compared to the next level. So overall, this implementation was very beneficial, and Yes.
Okay.
You have the base images have this is what you have